Hello everybody, it's Mrs. Pound, and this is our last video for Chapter 34 on electric current. Our objectives for today's video are to distinguish between direct current and alternating current, compare the drift speed of conduction electrons in a current-carrying wire to the signal speed of changes in current, compare the motion of electrons in a wire carrying alternating current to the flow of energy through the wire, and relate the electric power used by a device to current and voltage. So let's first talk about direct current and alternating current, what that means. Direct current is electric current whose flow of charge is always in one direction. This is the type of current that is produced in a battery as the electrons move from the negative end of the battery to the positive end. Alternating current is electric current that repeatedly reverses in direction twice each cycle, usually at 60 cycles per second or hertz in North America or 50 hertz elsewhere. So the current is not moving in one direction, it's actually moving in both directions and cycling back and forth. Electricity we purchase from power companies is AC, it's alternating current. Electricity is transmitted as AC power from plants to our homes because it can be transmitted great distances with easy voltage step-ups that result in lower heat losses in the wire. Uh, Direct current produces a lot of heat, and we're going to get into this more in another chapter, so I'm not going to get into it right now. The standard voltage in the United States is 110 volts or 120 volts. And the reason for this is because when they were starting to produce electricity, this is the voltage through light bulbs that produced about the same amount of light as gas lamps. Um, as technology was improved in Europe, they started electrifying everything later. So they actually used 220 volts in Europe because the technology improved. But we've stuck with 110 or 120 volts in the United States because we have all of the equipment. But we can operate 220 volt to 240 volt appliances such as electric stoves, air conditioners, and clothes dryers because your electric service has three wires: 120 volts positive, 120 volts negative, and neutral, which is 0 volts. Most appliances are connected between the neutral wire and one of the other wires producing 120 volts. So either the 120 positive or the 120 negative. So there's a 120 volt difference there. Larger appliances are connected to both the 120 volt wires, producing an overall 240 volts because the difference between positive 120 and negative 120 is 240 volts. Now, converting from AC to DC, there are many things that we use that do not use alternating current. They use direct current, such as a calculator. You might want to use a calculator running direct current. My computer, okay, runs off a battery most of the time, but it has to have a power converter on it. So how is that done? That's done using, first, I didn't mention it, but there's a transformer that lowers the voltage because my computer does not run on 120 volts. After it goes to the transformer, there are diodes. And you might be familiar with the term diode because we use light emitting diodes in flashlights. Now, this is not the type of diode, but I did put it in the background so that it would be like, oh yeah, diode. Okay. A diode is an electronic device that restricts current to flow in a single direction in an electric circuit. So remember, AC is going back and forth. Okay. The diode only makes it go in one direction. So what we do is we have to have two electrical components combined to convert AC to continuous direct current. So we have a diode to allow electric to flow in one direction. So here is our alternating current, our positive and negative voltage. It goes through the diode here, and on the other side, it's only in one direction, but that is really bumpy. It would be going off and on continuously. So, what they do is they also add a capacitor to store charge to smooth out the pulse. Now, capacitors just store charge. So, what it does is instead of having those bumps, there's a bump. The capacitor lets out energy until it gets to the next bump. It stores some energy, lets it out gradually to the next bump, stores energy, lets it out gradually to the next bump. And so it evens out that signal. So let's talk about the speed of electrons in a circuit because when we flip on the switch to turn on the lights, it happens immediately. So, how fast are those electrons going? Electrons move through a wire conducting electricity a few million kilometers per hour in random direction. So, they're not even moving in the same direction. That could cause a problem, right? But traveling through the circuit at the speed of light is the electric field. So it's not actually the electrons that are traveling at the speed of light, it is the electric field that is produced. It is energy that is traveling at the speed of light through the wire. Because actually, if we relied upon just the electrons to go through, it actually takes a few hours for an electron to travel 1 meter through a wire. So think of it like our waves. When we were talking about waves, remember, in the medium, like in the slinky, think of the slinky. It was not the matter that moved, it was the energy that moved. The energy was passed from particle to particle. And so that is what is happening with electricity. You are not receiving electrons at the speed of light, you're receiving the energy at the speed of light because it is passing it on to other particles. Now, a battery provides our direct current, remember, but in direct current, they will flow in one direction. But in alternating current, electron flow is simply back and forth going nowhere. So this also reinforces the fact that it's not the electrons providing us the energy. In direct current, you could maybe say it could be, but even they're flowing very slowly, couple like a meter over a few hours. But in the alternating current, they're not even moving. So it is the energy that is moving. So the source of electrons in a circuit is the power companies sell energy, not electrons. Okay? They are selling us energy, not electrons. The electrons that provide heat and light in a light bulb come from the bulb's wire filament, comes from right here. Okay? They are not from the power company at all. Like I said, it's just the energy to get them in motion and to provide that heat and light. So, electric power. Electric power is the rate at which electric energy is converted into another form, such as light, heat, or mechanical energy, or converted from another form into electric energy. We have an equation for electric power. It is current times voltage. And if we break down current and voltage, we see that current is charge over time and voltage is energy over charge. The charge cancels out, and so we get energy over time, which is also power. So we can use these interchangeably, current times voltage, energy over time. The unit is the watt, and it's 1 ampere times 1 volt. But that unit is just too small, really, for the amount of power that we do use. So in the United States, what we use is the kilowatt hour, okay, is the power company's unit for energy instead of the joule. And energy equals power times time. We're going to use this equation in class. So our objectives for today were to distinguish between direct current and alternating current, compare the drift speed of conduction electrons in a current-carrying wire to the signal speed of changes in current, compare the motion of electrons in a wire carrying alternating current to the flow of energy through the wire, and relate the electric power used by a device to current and voltage. So if you listened to today's video, I want you to go back in your notes and next to uh, the alternating current, I want you to draw two circles representing electrons, and I want you to just draw like a double-ended arrow over them, showing that they just go back and forth. They're not really moving anywhere. So that is it for this chapter. You have everything you need to start studying for the test. Don't forget your 5 questions, and we'll have another chapter on electricity.